All right, so I think we have done all the hard work. So now, I mean, today's lecture we can have some fun talking about information paradox and firewalls and things like that. So yeah, so let me first start with the lifetime of a black hole. Basically, that when we compute, we calculated the flux of Hawking radiation that is leaving the black hole in our last lecture, right? So the thing that we computed was basically this expression. So let me repeat that. We have so this is what we wrote down last time, okay? This is what the expression that we had, and this is what we called essentially, some gray body factor or whatever, which is related to the fact that when the Hawking radiation tunnels out through this angular momentum barrier, there will be some slight grayification of the black body spectrum that you see. Okay, so this is what we calculated last time. So this object we did not fully compute it, but it's in principle computable. It only depends on the actual potential, and it's essentially just a quantum mechanical problem for standard radial tunneling. Okay, so so this is in principle calculable, and people have computed it. It's only that the potential is not as simple as a harmonic oscillator. It takes work to do it. So, and this was, I think, done. There are some famous papers by Don Page where he computes it in great detail. I think numerically back in the day. Okay, so so what we are interested in is we just want to make an estimate of how quickly the black hole will radiate away. Okay, so we want to compute the total energy, that is energy flux coming out of it, and that's sort of easy to estimate because we already argued in like one of our earlier lectures that for high L modes the decay rate is the potential barrier is higher and higher, so most of the radiation is going to be in what are called the S modes, which is L equal to 0 modes. Okay, and we can just more or less dimensionally analyze. You can use dimensional analysis to justify this sort of an expression. And roughly speaking, it means that in order to the crossing time is if you know what the frequency is and if you know what the length of this the scale of the black hole is, this is roughly what the cross section would look like. Okay, so if you have a wave of some frequency or wave number and the size of the black hole is this, essentially the cross section is how many waves you can fit on top of it, right? So that's really what this is. Just the dimensional analysis, and the square comes up because it is it's a probability and not an amplitude. Okay, so that's the estimate, and this is you can justify it in whichever way you want. I mean, you can actually look at the potential and also compute it also, but whichever way you want, finally it is kind of a plausible expression. Okay, and the interesting thing about that is that, and we assume that we ignore all L greater than 0 modes. Okay, so we ignore all the L greater than 0 modes in this calculation, essentially because the potential barrier is high when L is higher, so most of the decay is going to happen in the S modes is the implicit assumption. And now this problem has reduced to what we already know. So if you make this assumption and plug that in, this has basically become a Planckian integral that we are familiar with. Okay, so this is an integral that you can look up. I looked it up today. I mean, if I had a more if I knew my physics better, I would probably know the answer. But this is pi 4 by 15. And I claim that this result is all that you need in order to do this. And at the end, you get some expression, which is basically just d by dt is minus 1 over rs square. Some constant is there here. Let's call it k. Okay? So this constant will depend on, it will depend on anything. It is basically a numerical constant essentially. Okay, so note that this beta is also proportional to Rs. So there is no other parameter in the problem. The only parameter of the problem is Rs. Okay, so that means that you can just change variables and you will extract an overall factor of 1 over Rs square, and then the rest is a numerical integral. Okay, so you'll do that and then you get some number. I don't know what that number is, but you can easily check what it is. Okay, so and the result, so this basically means that now this E is basically what you view as the mass of the black hole. Okay, and note that we have made a conceptual step there at that point. So before, when we did the quantum field theory in curved space type of calculations, we were essentially in the limit where the radius of the black hole is held fixed, but the mass of the black hole is infinite. Okay, because we are working in G Newton going to 0 type of limit. So in making this assumption, so now what we are doing is we are going one step away from it. Okay, so and this is a tricky step, but it's a reasonable step because, yeah, I mean, we can justify it in a few different ways. Assuming that the state that is coming out of the black hole is thermal, and we believe that our approximations are valid as long as the mass of the black hole is much higher than m Planck. Okay, so this is the assumption that we are making in order to do this kind of a calculation, because this is, the mass of the black hole is typically much higher than m Planck. Right? So, and if that is the case, we expect that the thermal state that you see is a good approximation, even if the mass of the black hole is changing. Okay? So, but it is a little bit more heuristic than the calculations that we have done so far. But nonetheless, it's believed to be reasonable. So, and then you can, if you believe that, then you can integrate it, and essentially you find dm by dt is, Rs is this thing. So it's proportional to minus 1 over m square, whatever. So you integrate it and you find that the T evaporation is of the order of m cube. Okay, and if you keep track of the g Newton, you will find that it is g square times m cube. Okay, so, and this again, that's just dimension analysis. If g square times m cube has a dimension of time. Okay, so, and this quantity is sometimes called the page time. Page time, or this order of time scale. This time scale is sometimes called the page time, because this is the time. So essentially what this means is that if you started with a black hole of mass m, how much time does it take for it to completely evaporate? Note that at the very end of the evaporation, our calculations will necessarily break down, because the mass of the black hole will be comparable to m Planck. Okay, but there is a long history that the black hole has. And so this final stage, let's assume that we don't know what that is, but let's assume that we are calculating only up to m Planck. Still the time scale will be g square times m cube. Okay, so, and this is basically what is, this order of time scale. This time scale is what is called the page time. So page time is the time scale in which the mass of the black hole changes by, let's say, an order 1 factor. Okay, so if the mass of the black hole changes by, let's say, a fraction, it becomes half the mass or half the entropy or something like that. So that time scale is basically called the page time. And the page time will play a crucial role, at least an important role in some discussions of the information paradox, because that's what keeps track of the information content in the evolution. Okay, so this is like a huge amount of time. This is much bigger than the time scale of the lifetime of the universe, for instance. So even for astrophysical black holes and so on. So this is largely, but of course, note that in order to get the trouble in making these calculations, to see a Hawking radiation or something like that, is really the difficulty of, pragmatically speaking, the difficulty is in making the black hole. So the problem is that, we don't know how to make a black hole other than through gravitational collapse. Okay, if you could somehow make a black hole, semi-classical gravity is perfectly valid even if you had a black hole of mass like 10 to the 5, or a few orders of magnitude bigger than the Planck scale. Right? Because it's 10 to the 5 is a pretty good approximation. We don't need to go to the ridiculous masses that astrophysical black holes have. But we don't have a mechanism for creating black holes, which are like when you have a small mass, like let's say a kilogram or something like that. So, but if you could create a black hole of that mass, Hawking radiation is still a completely trustable calculation. And in principle, you could experimentally test in the information paradox. Okay, so, and that's an important point, because the scales, tends to think that black holes are kind of an astrophysical object, but the calculations that we are doing just require a hierarchy between the mass scale that we are looking at and Planck scale. That's it. And that is not much. It can be a few orders of magnitude, and that's good enough, So that's something to keep in mind, but we don't have any mechanism for making black holes. That's the real problem. Okay, so that kind of brings us, so now that we have discussed Hawking radiation in some length, so the next, we already mentioned this before. We already discussed that, that gives us, also fixes the entropy. We discussed this many times, so I'll just write it, quickly. Okay, so the entropy of the, we have a natural reason, because of the black hole thermodynamics like formulas, we have a reason to think that the entropy of a black hole is A by 4G. Okay, and so the natural total entropy, or sometimes it's called the generalized entropy, is of a system, of a universe, if you want, is the entropy of the black hole plus the quantum fields or whatever fields that live in that space-time. Okay, so this quantity is the quantity that necessarily has to increase is a conjecture due to Bekenstein. Bekenstein's generalized second law. Okay, so this is generalized second law, and this is generalized entropy. And generalized entropy is an important concept. You might think that, oh, adding this S bulk is, like, obviously it's true. And it is kind of like, it was kind of treated as a, I would have not thought that it had such an important, implication. But what we have learned in the last couple of years, or last maybe 3 years, is that this quantity, when you apply it in a holographic setting, it is actually quite powerful, and it can, taking this expression, and not just this guy, seriously, can actually reproduce the full page curve of the black hole, and I'll explain what the page curve is later. So that's a partial resolution of the information paradox. It's not a complete resolution. The information paradox is still not solved. Okay, anybody who says otherwise is just saying random things, because we don't understand how information paradox. I mean, everybody says that. I'm not saying that. Like, everybody says that information paradox is solved. It's just that nobody agrees in some sense. So, but the point is that we need to understand. I mean, there are many levels at which you could try to think about it. So, so this this is one, getting the page curve back, page curve, or the fact that, entanglement entropy in a system, if it is evaporating means degrees of freedom are leaving the system and going somewhere else. So if that is the case, if you can compute the entanglement entropy of the black hole and the radiation, and then it should take a specific form. This is what is called the page curve. Okay, and I will explain that later in maybe in a next lecture or something. So, and this particular shape of the page curve, getting it back is part of the ingredients needed in order to resolve the information paradox, and at least in a not fully controlled calculation, we can show that happens. Okay, so that's the success of this was a cause of jubilation and victory in the last couple of 2-3 years, and my point is that in order to do that, it's not just A by 4G. The recognition that the total entropy of the system really must take into account this, in some sense, was crucial for this resolution. Okay, so. So this is Bekenstein's generalized entropy, Bekenstein-Hawking or Bekenstein's generalized entropy. Okay, so now we have all the ingredients to basically talk about the information paradox. So one might think that, okay, so if there was no evaporation process, if the black holes did not evaporate at all, then you could assume that, whatever fell into the black hole just stays inside the black hole, the mass of the black hole stays as it is. It's just that we don't have access to it in let's say, as asymptotic observers. Okay, so the information is stored locally over there, but we don't have access to that here. Okay, so this is something you could have believed. So, but this is actually, even that is actually somewhat questionable. I kind of want to emphasize that as well, because the point is that the black hole in the inside of a black hole, there is no there is no structure. It's the only place where you could store anything is at the singularity. At the singularity, you expect that there is some Planck scale stuff that is happening, and you will have to store all the information about the black hole at near the singularity in some Planck scale region, and that, as I will explain, is already it's not clear that is doable in any reasonable sense. So the question of what happens to something that falls into the black hole is actually quite a mystery. Even if purely classically, it's not completely clear what happens to it. So that's one statement, but at least you could believe that whatever happened to the black hole maybe stays inside, whatever, and the singularity, the magic, whatever. And then you could believe that, okay, we don't have to worry about things that you see. The fact that you're missing information when something falls in or makes a black hole is probably an acceptable thing, because you don't, at least you could believe that the thing is living inside and you only have access to the things there. But that is what goes away when you have evaporation. Okay, so when you have evaporation and you assume that the radiation is thermal and exactly thermal, then what happens is that gradually and steadily this the initial state, which we presume is a pure state, eventually becomes so at least until the black hole evaporates up to a mass of M Planck, it's definitely thermal, at least according to the the Unruh state that I explained to you last time. Okay, so the state that you're looking at is thermal. So, but when and the question is whether this last M Planck quantum effects can rescue this apparent thermality or apparent evolution from a pure state to a thermal state in some way. So that is sort of the question. Okay, so yeah, so let me just first say that up to m, mass of the black hole reducing all the way up to m Planck, Hawking's calculation looks reliable. I'll argue that, like I mentioned last time, this question of trans-Planckian modes, I'll elaborate a little bit more on that because I think it is, ultimately I think it is going to be important for various things. So so modulo that, if you grant me the untrue state as the outside state of a collapsed shell, then Hawking's calculation is reliable. So then there are three possibilities basically. So the first possibility is what is called the remnant. Okay? So the remnant is that you start with a pure state and you're radiating this apparently thermal looking density matrix mixed state in that state until the very final stages. So the question is, so what can happen at m Planck when the black hole actually becomes mass of order the Planck mass, right? And the idea of remnant is, I don't know whether anybody really seriously believes it. I think that remnant is probably the one that I think, well, I mean, I have seen a review on remnants, but I don't know whether even the authors themselves actually believe that remnants are there. But this is, I think, probably the one that I think most people do not believe. But let me start with that. So these are basically Planck-sized or Planck-massed leftover object. Yeah, so the problem with this remnant idea is that since the black hole that you started with was an arbitrarily large object, right? So in order to save information paradox, this object will have to be able to contain an arbitrary amount of information. This is what a problem with it is. So it means that there is some microscopic object which is of fixed mass but can contain an arbitrarily large amount of information. That already sounds suspicious and definitely is not something that it is. If it is there, it is really a kind of an ugly kind of. It sounds problematic already, right? And also, if there exists such states in the theory, you can argue. I mean, I'm not going to get into in details, but you can look up. I think there are papers by Giddings. I think it is Giddings, where he talks about the trouble with remnants and so on, and you can argue that if they propagate in loops, it will affect even infrared physics. Okay, so but I'll just leave it at the stage that there is an object which is of finite amount of mass, and small mass. Planck mass is not very high, right? It is just 10 to the 19 GeV, which is basically not, it's like, few joules basically. So, I mean, not, it's a reasonable amount of joules, but not crazy amount of joules. So that means that it's not clear that, so that seems quite surprising that amount of mass can contain an arbitrarily large amount of information. Okay, so that's one reason why people, it seems like just one reason, but I think it is a quite compelling reason because we don't know any way of arranging that, so. And it's note that its entanglement entropy should be roughly speaking comparable to that of the entropy of the original black hole. And so which means that as the original black hole's mass, the initial black hole's mass can be different depending on what black hole it started with, what this thing started with. So, and that means that it doesn't even have to get to m Planck for this to be problematic. So it essentially what it is saying is that as long as it starts evaporating, already its entropy or its the information content in that is already higher than the amount of information that the entropy that you might associate with that black hole. So what I mean is that let's say you started with a black hole of mass m, okay, so and it became a black hole of mass which is less than m, okay, by radiating. So, but the point is that let's say that it radiated no information. It essentially means that this object has to carry the entropy of the bigger object m. Okay, so already it's somewhat problematic. And I'm saying that you can make that problem very sharp by bringing it all the way down to m Planck, Okay, so you evaporates completely, almost completely. Yeah. Sorry?
The radiation has some entropy.
Radiation has entropy, and that's actually a good point, but very roughly, I'm talking about, I have to make a, in fact, it is actually true that the entropy of the radiation that you get at the very end of Hawking evaporation is actually higher than that of the entropy of the original black hole that you started with. Okay, so the final entropy of the system that's the reason why it evaporates, because the entropy of the final radiation is higher. But I have to be a little bit more precise, you're right. What I should really be talking about is the fact that it is a state counting entropy. So what this object has to have an entanglement entropy which should have a state counting interpretation. So, and that is hard to arrange when you have a mass of a black hole which decreases, and you, roughly speaking, I mean, this is a very crude argument, I'm not getting behind it too much, but I'm just saying that, initial configuration, if you really want to, what I'm trying to make a distinction between is that there is a notion of thermal entropy, and then there is a notion of entanglement entropy. Okay, so the thermal entropy, you are correct, will increase, but here when we are really trying to keep track of the information in the system, what you're really interested in is, in fact, the entanglement entropy as well. So, and that is what makes it difficult to arrange, because you're 100% correct that, if you just cared about the fact that the radiation was thermal, it is true that the final state has higher thermal entropy than that. And that's related in some sense to the information paradox, because what it is really saying is that the thermal entropy of a black hole, if as it radiates, keeps on increasing. Okay, but what you would like is that the entanglement entropy, you want it to turn back into this shape at a later time. By the time the evaporation completes, you want the entanglement entropy turned back, because let's say, I might as well, since a question came up, let me just say that, let's say you have two systems A and B, okay, and together they are in some kind of a pure state psi. If that is the case, SA is equal to SB, right? So the point is that if your degrees of freedom are leaving from here to here, at the beginning and end of this evolution, the system is in a pure state. So the entanglement entropy will actually be 0 in both cases. So, but in between, there will be some, because there is degrees of freedom or this thing, so it has to go up. So this curve should be taken sort of metaphorically. What it means is that it can have whatever shape it wants depending on the details of evaporation, but it should go up in the beginning and come back at the end. And that's what entanglement entropy should do. But like you are saying, the thermal entropy is always increasing in some sense, because it assumes some kind of a coarse grain. So you are assuming that there is some information that you're willing to give up when you're talking about thermal entropy. So you're not keeping track of the fine-grained entropy, you're keeping track of the thermal entropy. And that's why the radiation, as we were saying, has at the end of the evolution, it has bigger thermal entropy than this thing. But if you just look at the entanglement entropy, if the black hole is completely evaporated away, it should really be 0, because you have a pure state. Okay, so yeah, it's kind of a long-winded way of saying that this object, it's the thing that I'm emphasizing here is in some sense the entanglement entropy of the object and not the thermal entropy. So that's the only point I wanted to make. Okay, so anyway, so remnants are anyway. There may be a way to salvage remnants as an idea, but it is. Sorry.
Area of the black hole remains same.
No, when the black hole decreases in size, its area decreases, right? What I'm saying is that, but if you wanted to explain its entanglement entropy, because the radiation that left the system does not really contain information. So if you are really, interested in keeping track of information, so as you were saying, that the thermal entropy increases, but there is a sense in which that radiation does not carry any information. So the fine-grained information of the system, which is basically what is captured by the pure state that you started with, that information still has to be found here somehow. And I'm saying that is problematic, because very roughly you would expect the area to be, if you want to view the area of the entropy of the black hole to be associated to some form of internal state counting, that is hard to arrange here, because now the area is smaller, but you still have the responsibility of explaining this much information that was there. Okay, so I'm saying that the thing that I was trying to emphasize was you don't have to wait till it gets to M Planck to make the claim, make the argument about remnants being, you don't have to, even before that stage, you can make a case that remnants seem problematic in some sense. You cannot, it's hard to explain the information history of information very well if you assume, well, I mean, there are various assumptions that I'm making here and many of them can be broken. Or, there are various things, but I'm just saying at a very crude level, it already doesn't sound very plausible. And I think that probably among the three things that I would say, I think the remnants are probably the least taken seriously, let's say. Okay?
So does the variance in generalized entropy remains the same, or is ADS increasing?
So all of this depends a little bit on whether we are talking about the thermal entropy or the entanglement entropy. So this object, you have a variation of this. So the way I wrote this here, this is basically thermal entropy. And this I will kind of, this is something that, I was not sufficiently precise, but eventually we will have to be. So here, for instance, this is basically the thermal entropy, and that's why I'm writing this. Okay, so this is necessarily the case because there is an implicit coarse graining that is understood, and so of course, but there is a version of this which one can actually, use for entanglement entropy as well, and in fact that is the object that was used for this page curve discussion in the last couple of years. Okay, so but this at the level at which Bekenstein was talking about, this object was purely it's a more thermal entity. Okay, so that's what we will ever say about remnants. So now the second possibility, which is to declare in some sense failure, and this is the option that Hawking took in his sort of famous paper. Okay, so the information paradox paper, he just declared that okay, the final state is probably thermal. This is what he, this seemed to be the sort of the stance he took. So, and I think, so one of the big reasons why we think that that is probably not the answer is because we have ADS-CFT as an example of a quantum gravity. Okay, so I think this is one of the big reasons why people no longer believe that this is the correct answer. One of the big reasons. I mean, there are, in fact, the way in which people came up with holography as an idea was because, Toft and later Susskind believed that information loss cannot happen, and the way to arrange that, which is quite remarkable, even though it was a qualitative statement, it's remarkable that they kind of came up with the idea of holography as a way of rescuing information loss, even long before ADS-CFT was discovered. Almost like, 7 or 8 years before, I think. Okay, so ADS-CFT, the reason, and I'll tell you why ADS-CFT, kind of forces you to believe that information loss doesn't happen. The reason is that ADS-CFT is a theory where you have this. ADS-CFT is basically telling you that there is quantum gravity in some space-time, which is ADS, is dual to some conformal field theory. Okay, so these two theories are the same, but conformal field theories we know by construction are unitary. So, and black holes, have natural analogs of things called plasma balls or configurations in CFT. Okay, and so there is nothing in the CFT that allows information loss. So, and because of which there must be a mechanism that unitarizes Hawking radiation is what we believe. Okay, and note that, but this is not quite. So you could say that this is sort of the strongest argument for believing that information is not lost. But at the same time, it doesn't really constitute an explanation or an understanding of how information comes out in the bulk language. Okay, in the gravity language, it's still not solved. That's what it means to say that information paradox is still not resolved. Okay, we don't understand in the gravitational degrees of, so if the statement is that ADS quantum gravity is the same thing as some conformal field theory, which is basically just some unitary Hamiltonian. Okay, so some quantum field theory. So the problem is that in this there are some configurations in this which we call black holes which have dual configurations, and there it is more like a burning piece of coal. Some state which thermalizes, and then that's essentially what the analog of this phenomenon would be. And even if we don't know precisely the map, and I don't think we understand the map from black holes to the CFT states very well either. But it's clear that there exists something which is dual to black holes, and because the CFT is unitary, we don't have to know anything about how the process happens in order to say that information somehow must come out. Okay, so that's the sort of the ADS-CFT answer to information paradox. But of course, so that some people will say that that's a resolution of the information paradox, but that is it's not a satisfactory resolution of the information paradox in the sense that we need to understand what is wrong with our bulk argument before we can say that we have completely understood it. Of course, it gives us a good confidence, but it's not the same thing as saying that we need a bulk understanding of how the information comes out, and that's the sort of the third alternative. So, sort of the preferred is that there is some kind of subtle correlations in the untrue state. Subtle correlations in the untrue state. Okay? So the claim would be that, so the untrue state, if you remember, was like, so the rho untrue, so which is the state that was outside the black hole, outside after the shell had gone in, the state that was there. So this state is basically we had, so something like this. So this is what I wrote. So this was ingoing, and then there was, I'm not worrying about the normalization. So it was something like, should also put like omega. So outgoing. So this was roughly the structure of the state. And this point is that this is a thermal density matrix. So that is the root cause of all information loss. Okay. So this is what we assumed. So the claim of this preferred sort of subtle correlations idea is basically that what you do is that so this basically means that you have a thermal density matrix sitting here, right? Instead of a pure, this is basically a pure state, but this is not. Okay, that's where information loss is coming in. So the way in which one thinks about that is that this state that we wrote down for the radiation that is coming out of the black hole. So let me just again draw that picture that we had last time. So this was our shell, and this radiation this is the eventual Hawking radiation. So there is some modes going this way, and then there is some modes coming here. So this state at this point and this point is what we are put in here. Okay, so this guy is the vacuum, and the stuff coming out of this guy is basically a thermal density matrix. So that's the claim. Okay, so and together that gives a complete set of modes for the initial state there. Okay, so that's what we did. So, and this thermal density matrix, so the claim of something like, when you say there is subtle correlations, what it means is that you are exploiting a statement about Hilbert spaces of complicated systems in quantum mechanics or quantum gravity or quantum anything. Okay, so the idea is that, let's say you have, let me not explain what this is. It's some extremely, if you have a complicated system, which is, let's say, chaotic. Chaotic means anything that causes thermalization. Thermalization is the idea that complicated systems basically interact among, its ingredients, and in some, finally it will basically look like a thermal state. Okay, so this is the intuitive idea of thermalization. Any complicated sufficiently high energy state is, so let me call this, let me call it a generic heavy state. Generic heavy. Heavy just means it's a high energy state in the Hilbert space of whatever theory you're looking at. Okay, heavy is not in the sense of gravitational heavy or anything. I'm just saying that whatever theory it is, if you have a sufficiently energetic state, and I'm not saying that it's an eigenstate necessarily even. Okay, so it is believed that what I'm saying is true even for eigenstates and chaotic systems. Okay, it is believed that it is true, but I don't even have to assume, because let's say that there is some generic state. The Hilbert space is, it's huge. Right? The general set of space of, if you have a set of bases, you can construct very general states which are superpositions of all the basis elements. And the Hilbert space is in some sense a huge amount of, huge number of states are available in the Hilbert space. So let's say you are considering some given generic heavy state. Okay? So the claim is that for large classes of simple operators in the theory, so simple operators you can think of as, roughly speaking, a scalar field in Minkowski space, for instance, or a spin in an Ising lattice. Okay, so those are all simple operators. But you could construct something which was like, a huge chain which is constructed with a huge number of sigmas. You could construct that. That's not a simple operator, that's a complicated operator. So note that the notion of a simple or complicated operator depends on the theory that you're considering. Okay, so in particular, it assumes a particular tensor factorization of the Hilbert space. So when I say that a small operator in the Ising Hamiltonian, in the Ising system, so if I changed my basis to something that was a complicated, some complicated mixture of all the spins was my basis, then my spin may turn out to be some complicated operator. You know what I'm saying? It's the same sense that entanglement depends on basis. So if you change the basis, sometimes the states which looked entangled may not be entangled. Is that clear? So in that exact same sense, the notion of a complicated state or a complicated operator depends on the Hamiltonian that you're looking at, and whether there is a natural notion of simplicity in the ingredients that the Hamiltonian is made of. Okay, so and these are somewhat let's say important ideas, especially in the recent context of discussions of locality and all that. So essentially what you want is that a theory like Ising model basically has a local Hamiltonian, and you're looking at the local pieces in order to when we talk about simple measurements, simple observables or simple operators. Okay, so in the case of the simplest example, let me write. Ising model is always a good thing to keep in mind. Okay, something like this. Okay, so and I'm saying that this assumes, so this Hamiltonian I could have just written in some general basis of this Hilbert space. It would look like a mess, right? If I is going from 1 to n, let's say it's a finite lattice size, and this means that there will be 2 to the n. The Hilbert space is 2 to the n dimensional. And I could do an arbitrary horrendous change of basis, and this Hamiltonian will be some terrible matrix, whatever, like some with all kinds of real, real numbers in it. Okay? So, but on the other hand, this particular structure means that there is something special about this Hamiltonian. There exists a basis when it can be written in this way. That's what it means. So that's a non-trivial statement. Okay? And in this kind of a setting, what I mean by a small operator is basically something like sigma I. So if you change basis, what becomes simple and not is not very clear. So this kind of the fact that such a basis exists for a theory is not always clear. So but it's sometimes called, if it exists, it is called a local basis. Okay, so spin is a local basis for the Ising model. Okay, is that clear? So the general story, I mean, I'm not really, so the general story is very important, because otherwise that gives you some kind of an orientation on how to think about these things. Okay, so the point is that now I want to come to the main sort of statement that I want to make, which is that
I don't understand how two states which seems entangled in one basis are not entangled in another basis. Like, are they entangled like we normally say that these particles are entangled or something?
Sorry?
We normally say that two states are entangled, so it is basis dependent or?
It's basis dependent.
It's basis dependent.
It's basis dependent, right? I mean, for instance, it's really the question of, see, the fact that a state is, what is a good way to say? So I think a good example would have been better, but I think that if I try to write some entangled state, I think I'll just screw it up. So the point is that, like if you go, for instance, there are people who talk about this plus, like instead of working with up and down, you could work with a linear combination of those, and you can you can try around with some specific simple examples, and you will see that states which look entangled in the let me call this and this. Okay, so these two states. Okay, the claim is that you can construct general states in tensor product Hilbert spaces. Tensor product means you need to have one for this and one for this, or one for like you should look at states which are made of and the other four. Okay, so this is a tensor product Hilbert space. The claim is that you can find states in that tensor product Hilbert space which are entangled in this up-down basis but are not entangled in this plus-minus basis. So that you can try to, there are simple examples exist, but I don't remember, like I don't want to spend time on it. But there exist simple examples of this. So this is basically an example of a change of basis. Okay, so you take some state in this Hilbert space. The claim, it's not that some of them may not be, but there exist such states is the only statement. Some of them might be that, like both of them have similar properties in both bases. But what I'm saying is that there exist states which are entangled in one basis, which need not be entangled in this. So that is basically the statement. So that's the reason why it is, if you change the basis that you're working with, entanglement can go away. Okay, so entanglement is not a fundamental property in some sense. It is a property of how you look at pieces of the Hilbert space. So, and what you are looking at is sort of your choice in some sense. Okay, so so that's the statement I'm making. So that's why I said that this, this simplicity of your Hamiltonian that you have here is a statement about the specific tensor factorization or the specific local basis or the specific spin system that I'm thinking of for writing this Hamiltonian. I could write it in some other basis and it will become horrible. Yeah.
So how do we know that this kind of basis are exactly in the system doesn't like it?
That's a different question, right? I mean, yeah. So I mean, it can exist. It's in general, it will always exist. So yeah. I mean, I don't know. I didn't understand the question. Maybe.
Like if we have some angle in it, you cannot believe that.
Mm-hmm. Oh, I see. So yeah, there are these quantities that you can write down. For instance, like an example is, there are various quantities that you can compute which will be non-vanishing only if the state is entangled. So there exist states, so for instance, this state that I have written down here, there is no basis in which it is not entangled. You see what I'm saying? So, or more precisely, the density matrix of this is that, this is obviously a density matrix, not a pure state. But what I'm saying is that this state, is always mixed. You know what I'm saying? I mean, I'm not saying it well. So it's clear from this that if you look at the diagonal, this thing, it has, and no matter what you do with the basis change, it's not going to accomplish anything. What I'm saying is that. So basically what I said is that the notion of entangled, the notion of entanglement of a state is basically very much reliant on the basis that you're working with. That's all I'm saying. I'm not saying that, this state, for instance, is definitely it's not a pure state, no matter what you do. Okay? So that statement that I made doesn't refute this observation. These are two simultaneously true observations. What is that quantity?
What is that quantity that you?
For example, there are many. I don't think it is known a full characterization of all such things, because it's kind of like you need to compute some quantities. Is there I think it is, the following statement is at least, I don't know that it's 100% true, but it's something like that is probably true, which is that, there might, I don't think it is known what is the complete list of, let's say things like entanglement entropy that you could write down for a given state, which characterizes unambiguously whether the system is entangled or not. I don't think it is known, but maybe I'm wrong, So yeah, I think that's the best I can say. But I think that, yeah.
Like when you say that like some state are entangled in one of the bases and become unentangled in other bases.
Right.
So that might also be happen that the state which are unentangled in that basis may become entangled in the.
Sure. I mean, if you go the other way.
So I think the entanglement is somewhat being conserved in that sense.
It's not conserved, right? When you change basis, it actually becomes unentangled.
No, but some other state which are unentangled in that basis become entangled in the basis that we change.
Sure, yeah. I mean, but we are looking. So that's basically just a property of the Hilbert space in some sense. It's not a property of the state, right? So the Hilbert space, I agree that some states will go from entangled to unentangled, and it'll go from vice versa. But I'm saying that if you're looking at specific states, the entanglement is a property of a state. So, and if you're talking about a property of a state, I'm saying that it's not conserved in the sense of if you change basis, you might be able to get out of being entangled.
But overall, Hilbert space entanglement that we have, it's
yeah, I mean, Hilbert, also it depends on what kind of tensor factorization that you're assuming, right? You could choose to work with, not necessarily with qubits, you could choose to work with, let's say you have a 2 to the 2n dimensional Hilbert space. You could choose to work either in the qubit, 2n qubits, or you could choose to work with some other, let's say, some 4-bit tensor factors. So all of these things are possible. So the choice of tensor factorization is fundamentally related to the theory that you're looking at. So that's what sort of decides, because all Hilbert spaces are sort of isomorphic. It's not very, like if you fix the dimension, all Hilbert spaces are the same, right? There is not much structure in it. It's huge, by the way. The sort of the phase space or the number of states that are there in the Hilbert space is huge because you can take linear combinations and so on. But at the same time, what is sort of interesting about the local structure of the theory is basically the fact that there exist some Hamiltonians sort of which kind of breathe life into the Hilbert space and make it into some local structure. So if you just write down a random Hamiltonian in some random Hilbert space, it's some mess. It will not have any interesting structure. So, but what is surprising about the theories that we seem to find in nature is that they often seem to have this locality structure. So they seem to allow a particular tensor factorization in which the Hamiltonian takes some simple form. Okay, so that's what makes it interesting.
So the eigenvalues and the eigenvectors that we compute are with respect to these local operators.
So eigenvalues and eigenvectors define a basis for you. Right? It is that once you compute eigenvalues and eigenbases, you don't really know anything about the local this thing, right? So the locals, if you write down this for let's say an n of some n equal to 4 or 5 or something like that, and you try to diagonalize it, that is some you will get a matrix which is 2 to the 4 times 2 to the 4, and it will be diagonal, and you will get a set of basis elements which is a column vector. Right? So, but that doesn't immediately know anything about the original, the local basis that you talked about. Because by diagonalizing the Hamiltonian, you're going into a new basis which does not know anything about the tensor factorization that you're working with. So the tensor factorization of this guy here is basically saying, oh, there is a specific notion of spin. So once you diagonalize what is this guy's name? Ising model. So once you diagonalize an Ising model, it doesn't know anything about spins. It basically knows the state and the eigenvalues. So the spins are all gone. The information about spin is gone, right? So of course you could, there are more things one can say, but I'm saying that the base diagonalization defines a basis for you, and it's not immediately, this is some other choice of basis. Okay, so
the elements will be unique. Whatever.
Yes, the Hamiltonian's diagonal elements will be unique because Hamiltonian is fundamentally just a matrix. So which means that if you diagonalize it, its eigenvalues are unique except for permutations. Okay? So, yeah. Okay, so anyway, so these are all kind of digressions, but the thing that I wanted to say was that it's a property of big complicated Hilbert spaces that if you compute expectation values in some complicated generic heavy state, they look approximately thermal. Okay, so this is a fact about generic Hilbert spaces which you can, in generic cases, for instance, you can show. This is actually, there are various levels at which one can prove this. So this sort of statements are what are called thermalization.
This is not later types.
Sorry?
This is not later types like T-types.
Not necessarily. Not necessarily. I'm not talking about time evolution yet, right? I'm just saying that there exists some typically it is true that if you start with some simple state and if it's a complicated, chaotic Hamiltonian, as time evolves, the state will tend to a complicated state. That is true. But I'm making a statement about complicated states. So if you have complicated heavy states in a system, if you compute its expectation value of some simple operator in that heavy, that complicated state, you can expect this. Okay? And this beta effectively will be determined by some properties of that state. So this, if roughly speaking, it's, you can, the same way in microcanonical ensemble to canonical ensemble transition happens. So, microcanonical ensemble is you're fixing typically energy, but there is a way in which you can go from microcanonical to canonical, right? It's loosely similar, but the point I want to make is not about that. Don't want to get distracted into things which are about how you get this thing, because how you get this statement. So, but the point is that this is true. Okay, and as I said, there are various levels at which you can make the statement. This is in fact true for generic heavy eigenstates of with chaotic systems. So in that context, this is sometimes called eigenstate thermalization. So I'm not talking necessarily about eigenstate thermalization. I'm talking about a weaker form of thermalization, if you like, which is basically that generic heavy states. Okay, so you can think of this like, let's say if you have a Hamiltonian and the spectrum of the Hamiltonian is characterized by some energy E. Okay, I am looking at, if you want, a microcanonical sliver of states in this system. So I have some E naught and E naught plus delta, where delta is presumably small compared to E naught. And in this there will be a bunch of eigenstates. Okay? So generally speaking, chaotic systems have fairly dense eigenstates in some suitable sense. So I take some arbitrary linear combination of the eigenstates living in this sliver. So, and that's what this generic complicated state is. Okay, so and in the quantum mechanically, the way in which microcanonical thermalization works is that such generic complicated states that you write down, this linear combination of eigenstates that I wrote down, linear combination with some arbitrary, freely, randomly chosen coefficients. So if I do that, this statement is true. This is the observation. So this is how thermalization happens, or this is how the microcanonical ensemble is defined in some sense in quantum mechanical theories. Okay, so the claim, so in order to salvage so in some sense, I mean, this is kind of like the simplest, the resolution of Hawking's calculation, the Hawking's information paradox. If you want to make this statement about subtle correlations, what you're really saying is that you're ignoring, so this some complicated heavy state which has a lot of structure, we are completely ignoring it and replacing it with this thermal density matrix here. That's what the Unruh state is doing. Okay? So instead, we should work with the full complicated state. Note that this is at this point is just wishful thinking. Okay? We are just saying that instead of this thermal state, there may exist some complicated heavy state which is approximately thermal. Okay? And Hawking's calculation is not resolved enough to detect it, because Hawking's calculation is essentially working with free theories, and whatever we discuss can actually be thought of as the level of statements about 2-point functions. Okay, so essentially we are just propagating free particles in some sense. So the only information that we are actually dealing with here is 2-point function information. Okay, because free theories, the only not trivial correlation function is a 2-point function. Every other correlation function can be built from it. Okay, so since we are working with free theories, that's the only information that we have. So this is the way in which we expect, this is the modern perspective on the information paradox, and this is what we think is true, even though a fully satisfactory way in which we can get that from quantum gravity is not yet known. Okay, so any other questions? So that's my brief discussion of information paradox, I think. So okay, so we went a little bit. I wanted to discuss scrambling. Yeah, I'll just say. Yeah, so I'll make two closely related statements. I want to talk about scrambling time, or which is very closely related to what I talked about last time, about Transplanckian modes, the problem with Transplanckian modes. So both these things are extremely important for all the discussions that we will have about firewalls and so on. Okay, Transplanckian modes. So scrambling time is basically the physics of the scrambling time is the same thing as the physics of the Transplanckian modes. Okay, so those are just two words of the same thing. So the point about, and I will also talk about firewalls, what people mean by firewalls. So those are the two things I want to talk about today. Hopefully we'll be done by 12. So, okay, so let me draw a picture here. Okay, so it's not very important for any of these discussions whether I'm working with Kruskal or with collapsing geometry, because I will always be concerned if it is a collapsing geometry, you can extend this, you can just look at it this way. I will only be dealing with things that happen here, so it won't really matter. So I'll just draw a Kruskal for concreteness, but anything is fine. Okay, so now what we want to do, so we want to look at a light ray that falls in, and this is a t equal to 0 slice. Okay, I'm choosing my time coordinate. I have freedom to do it because you can shift it, right? So I just choose it so that the picture here looks nice. So t equal to 0 is this slice, and this is some infalling, you can think of it as a shell, if you like, the shell that formed the black hole. Okay, so if it is really want to think of it that way, I have to change this picture a bit, but for discussions that are happening above this, it doesn't matter. Okay, so this is my t equal to 0 slice. And I want to look at, times which are, let me call it t out, which is very late times t out. Okay, I want to look at time scales which are very, very, very late time behavior of the black hole. The idea behind that is that I'm looking at after the black holes, all the trouble and the mayhem that caused the black hole or made the black hole has settled down. So once it is settled down, so that's the only purpose of making T out very large. So that means that the only radiation that I will get here at that stage is basically Hawking radiation. Okay, all the transient phenomena have died down. The black hole is in its final state. There is nothing else in this universe. So you will basically just Hawking radiation. Get Hawking radiation. So that time slice will be some time slice like this. Okay, so this is T out. Okay, and in particular it is much, in time scale wise, it is much greater than the Schwarzschild length scale, if you like. I just want it to be very late. So because this is the only other time scale in the problem, so I just want to be bigger than that. That's it. So, or immediate time scale. There are various time scales you can define. So this is the time scale in the problem. So the question is, so let's say you have a Hawking photon that is coming this way, and so I want to know, so this is the location of my potential barrier. Okay, so it's not a very good picture. Okay, so this is the location of my, so the potential barrier, it's basically at some fixed R, right? The potential barrier has a peak at some fixed R. It doesn't really matter whether I'm looking at the peak of the potential barrier. I just want to look at some fixed location R in the exterior geometry. Okay, so the claim, and then I want to see, so the Hawking photon that leaves, that crosses, the outgoing Hawking photon that crosses a potential barrier at a late time T out. So this is basically an ingoing photon or ingoing light ray, just to, light shell, null shell, the thing that formed the black hole, if you like. So this is the null shell that crossed the potential barrier at some particular time. Okay, you don't have to think of it, if you're worried about the fact that, okay, if the null shell is the thing that formed the black hole and, okay, the potential barrier happens only after the black hole is formed, etc. You can just think of it as some light ray going into a classical geometry. Okay, so, and then this is so it crosses here, and then I have a light null ray coming from here. Okay, so the point is that this is a Hawking photon, and this is, you can think of as an ingoing shell, light shell. So the question is, what is the time scale at which this guy, this light ray would have intersected, this Hawking photon would have intersected with the ingoing shell? Okay, so and that time scale is basically what one calls. Okay, let me just write it. So this is, so I have another radius. This is the R corresponding to R potential, let me call it R peak of the potential, and this here, this is basically this thing here is the location at which the collision between the two guys happen. Okay, so it's a bit complicated. So the point is that this is the peak of the potential or some fixed location I'm looking at, and this is the radial location at which an outgoing Hawking photon hits the ingoing guy. And what we are really, so let me just tell you what we are trying to argue. We are, so the point is that as T out becomes large, this goes to essentially a constant value. Okay, constant value, or at least it gets closer and closer to the horizon. And it gets closer and closer to Planckian horizon. So the claim is that R collision by Rs is approximately 1 plus. So this is the claim. So this is something that just from geometry you can compute this. Okay, so these are all, this is a null geodesic, this is an ingoing null geodesic, this is an outgoing null geodesic, this is some T equal to 0 slice, this is some T equal to T out slice, and this is some R equal to R peak, which is basically the place where the potential is peaked. It doesn't have to be, it can be anything. Note that the final answer doesn't depend on it. Okay, that's an important point. So that's the reason why I don't care where it is actually. So it just means I'm looking at some particular location. But the point is that these collisions are happening basically very close to the horizon, because this is an exponentially small quantity as T out becomes small, as T out becomes large. Okay, and this distance away from the Planck away from the horizon, it's essentially what one calls the transplanckian region, or the stretched horizon region of the black hole. So if as long as this distance is becoming Planckian, then you say that this collision is happening at a transplanckian distance away from the horizon. Okay, so that's what I meant by the statement in my last lecture, that the Hawking photons that you see at very late times are the photons that were straddling the horizon, very close to the horizon, and that's how they took a long time to escape. Okay, so when the black hole formed, some shell or whatever formed, and there was some incoming photon from the past, whatever, wherever, we don't really care where the origin of the photon was from. So, but wherever it came from, so this is the picture I drew last time somewhat badly, but let me draw it again. So I know that this is a bit technical, but I think after that firewalls, I promise will be easy. So the picture that I drew was, I think, something like this, right? So you had some, so the thing was, there were these null rays which were getting trapped, so these are null rays that are coming from somewhere, but they almost got caught by the black hole, but they didn't. So, but because they almost got caught by the black hole, they straddled the horizon for a long time before they escaped. So those are the guys that we are really talking about here. Okay, so and these guys, the claim at the end is that if you wait long enough, and if you are waiting after a long time and picking up your Hawking photon, they would have collided with this guy at some early time. And you can show by computing redshifts and so on that because note that this is in the asymptotic region. This is, even though this looks, both of them look kind of close to the horizon in this picture, but that's a trick of the Penrose diagram. This is really far away. This is far away in the asymptotic region, or picking up a photon, okay? Asymptotic observer. So, and there is redshift that has happened. And using this factor, you can compute the energy of the photon for some small energy here. Let's say you picked up some small energy for the photon here. You would see that this is always transplanckian. Okay, and that's kind of obvious because essentially there is a huge redshift happening at the horizon, and this photon is climbing out of it, right? To reach you at infinity. So, and that's basically sometimes called the transplanckian problem. And because this collision with the original shell happened at a transplanckian energy, it's not clear whether it is thrustable or not. Okay, because there is some local collision that happened between, it doesn't even have to be the shell that formed the thing. It could be some transient infalling thing that happened to the black hole, and that object can have a fairly low energy, but still this collision can become transplanckian. Okay, so so whether this invalidates Hawking calculation is a question. I feel that it is, I mean, the way in which people explain it away is usually by saying that, oh, okay, this is a feature that I'm working on because the Schwarzschild time's here. Okay, this is a Schwarzschild time that I'm working with. So that's the reason why, I could, in principle, completely avoid this problem by working exclusively in Kruskal coordinates, and then talk about, just essentially don't address this problem. People say, essentially that's the statement of Hartle-Hawking. When you say that the Hartle-Hawking state is, a pure state and it constitutes a smooth horizon, just like Minkowski space vacuum constitutes a smooth horizon, Rindler horizon. In the same exact sense, let's just assume that is the case. Okay, so that's, not assume, in the Hartle-Hawking case, it's a defensible statement. There we are not really addressing this problem. But note that this is a physical process. Okay, you're picking up a photon, and in principle, if you look back in time, it could have collided with something that was transplanckian. So, by going into Kruskal coordinates, what we have really done is that we have avoided looking at this problem. So, it is also, it's generally, I don't think people are, I think most people would say that the transplanckian issue is not completely settled, is what I would say. Okay, so I think my claim about the collective consensus of the community regarding the transplanckian thing is that it is a problem, but somehow we choose to ignore it because the thermal result that you're finding for the Unruh state is, despite that, somehow reasonable. You understand what I'm saying? So one of the reasons why I believe that is because black hole thermodynamics, all of these things tie very nicely with all the rest of the physics that we know. ADS-CFT, this, that, everything, So, but this particular piece in Hawking's calculation of this, the fact that, if you want to really phrase this in the language of a collapsing shell, this is a complicated, and, this is a question that is, whose resolution, in my opinion, is unclear. Okay? But as I said, one can bypass this like we did for the Hartle Hawking state. Just not address this issue. Just just work with you assume that the Euclidean path integral prepares a nice state for you. Okay, so note that here the preparation part is what is getting screwed up because you had a shell that had coming in. The initial state is more messy. Okay, so that's where this real problem is happening. But when you use a Euclidean path integral to prepare a perfectly entangled state, which we assume is entangled in the left and right inner wedge, and which has a smooth horizon, this problem is something that you can sort of avoid dealing with. Okay, so that's one way to explain it away. But nonetheless, as I said, there is a physical process issue here, and I was looking at Harlow, and Harlow also sympathizes with this issue as a physical problem. So I think that might be the consensus view, because I saw it in Harlow's lecture as well. Okay, so
How does this collision affect the final thermal radiation?
So it doesn't really affect anything. What it really does is that you're assuming that there is a collision that happened here, or in principle a collision that could have happened, which you're sort of ignoring. Right? What you're really saying is that this photon that started with, if you trace it back to its origins, then you have to worry about a trans-Planckian collision. Whether you are, whether you say that it is acceptable, Hawking basically says that it's okay. But the question is whether it is not, which is not very clear, because we are dealing with physics which is, quantum gravity related. So whether there was some problem with that, etc., we don't know. So that's the statement. So, and this went into the assumption that the Unruh state is thermal. Right, so effectively, in some sense, yeah. So that's the reason why it is something that one, at least, I agree with you that the result is thermal is reasonable, but at the same time, this is a problem. This is this is an issue that one might worry about, and that's the problem of trans-Planckian modes. So and the second thing I wanted to say was that this time scale, more precisely, I think T out by Rs. So let me make the definition precise. So this, so this gives me a time scale, right? So when this R collision is approximately L Planck, so you say that Rs by L Planck, so this, this whole guy here is an L Planck away from it. So essentially I'm saying that this is almost L Planck, okay? Rs times this is almost L Planck. So let me write it like this. Rs times e to the t scrambling by Rs is defined to by L Planck. So we introduce a new time scale here. Okay? So using the fact that this number basically shows up in some particular way. So the time scale after which this, so essentially this is the time scale after which if you move it out by, if you move by this much time in the exterior Schwarzschild geometry, you are already close to the, closer than a Planck distance from the horizon. Okay? So this guy will basically pick up information, or if you move it back, it's basically that's the time scale that you find. Okay, so this time scale is sometimes called the scrambling time, and the idea is that whatever instabilities that were there die down by this time. Then after that, it is basically just Hawking radiation. That's sort of the picture.
So in this picture, where is the T scrambling? Is that the?
It is the T out at which this roughly becomes L Planck. I'm taking out a factor of 2, but apart from that. Okay, so at this T out at which this becomes L Planck. That is what is called scrambling time. So essentially that means that at that point onwards, so if you wait that much, so the collision with the incoming shell happens closer than a Planck length to the horizon if you wait for a T out that is bigger than scrambling time. Is that clear? So you are closer than a Planck length from the horizon, so there is an incoming shell. So the incoming shell collides with, your Hawking photon collides with your incoming shell. If you are looking at the Hawking photon just a scrambling time after this shell went in. Fine? Yeah. So that's why it is roughly speaking a sort of a stabilization time of the black hole. Black holes, all the stuff has settled down, and then scrambling time is, that's actually a good question. So we can evaluate that, right? So LP by S scrambling, LP by RS. So So this is what T scrambling is. So I think it is a quick time. Essentially, I mean, it's a very quick time compared to, I'm trying to understand whether it is, what is physically, what is the exact, how quick is it, I don't really know, but it's a fast time scale. Roughly related to the fact that the black hole thermalizes very fast. Black hole is a thermal system in some sense, and it basically thermalizes very fast. That's roughly the idea, but yeah, I don't know exactly. I think you can plug in. Which one? Yeah. So this, you can compute it by putting in, let's say RS is 1 kilogram or, 1 something meter or something. And it's basically about, yeah. So you can check. Huh?
Isn't delta really small?
Yeah. So it's scrambling of.
Maybe I defined it wrong. So LP by RS. So what is the time scale? I think it should be fast, is what I would imagine. It's a good question. RS times log RS by LP, right? So L Planck is what? It's 10 to the 19, so it becomes like 19. Yeah, that's a good question. So I think maybe it is, it's off the, it doesn't seem very far from the time scale associated to the Schwarzschild radius. That's essentially what you're saying, right? So this times, let's say, a factor of 20 or something. So it's not that long a time. So yeah, maybe that's what it is. Yeah, I didn't know how. So yeah, it's supposedly a fast time scale in the black hole setting, but it's definitely fast in the sense that it is much smaller than the page time. The page time is very large because a black hole lives for a very, very long time, right? But yeah, so this is it's a fast time scale, but fast not in the not in the sense of like the laboratory physics, I guess. I mean, that's what the calculation is telling me. So I'll confirm that later. But it is a fast time scale, but compared to the page time, let's say. So how much time do we have? I just wanted to talk about firewalls, and then we are kind of done. So I'll just quickly go through firewalls. So firewalls are, well, I mean, maybe I'll do that next class, because I think Apurva has a class here at 12. Okay, so I think you can close it.